Hey fellow nerds, today we are going to learn full wave rectifier. We'll start with some design challenges, then we'll design a center tapped full wave rectifier, after which we'll design a full wave bridge rectifier. Then we'll take the rectifier with smoothening capacitor and a load. Finally, we'll have a comparison between half wave rectifier, center tapped full wave rectifier, and a full wave bridge rectifier. Let us start with our first challenge. This is my input. It is a sinusoidally varying voltage. And this is the output I want. Now, this is not even a challenge for you because this is exactly the output of a half wave rectifier. All you need is a half wave rectifier circuit. In the first half cycle, voltage is positive. So we get positive here and negative here. The diode will get positive here and negative here. It is going to be forward biased. Assuming ideal diode model, we can replace this by a closed circuit. Here the entire input voltage will be dropped across the resistor. So the output is going to be equal to input. In the second half cycle, voltage is negative. So we get negative here and positive here. Diode will get negative here and positive here. It is going to be reverse biased. So in the circuit model, we can model the diode as an open circuit. Since the circuit is open, no current is going to flow through the resistor, which means according to Ohm's law, potential drop across the resistor is 0. So the output voltage is going to be 0. In the first half cycle, output is equal to the input. In the second half cycle, output is equal to 0. And this is exactly the output voltage we wanted. Let us go to the next challenge. Here in the first half cycle, I want the output to be 0. In the second half cycle, I want the output to be equal to the input. Before we go to the solution, it will be better if you pause the video right now and give yourself a moment to work through the design. Here, the output is exactly the opposite of the output in our previous challenge. So all you need to do here is take a half wave rectifier circuit and change the direction of this diode. Now, in the positive half cycle, voltage is positive, so we get positive here and negative here. The diode will get positive here and negative here. It is going to be reverse biased. In the circuit model, we can model it as an open circuit. Here, since the circuit is open, no current will flow through the resistor, which means the potential drop across it is 0. V output is 0. In the second half cycle, voltage is negative. We get negative here, positive here. The diode gets negative here and positive here. It is going to be forward biased. So assuming ideal diode model, we can model it as a closed circuit like this. Here the entire input will be dropped across the resistor. So V output is going to be equal to V input. In the first half cycle, output is equal to 0. In the second half cycle, output is equal to input. This is exactly the waveform we wanted. Let us see the next challenge. Here, again, I want 0 for the first half cycle. In the second half cycle, instead of this, I want this. That means in the first half cycle, I want 0. In the second half cycle, I want output to be equal to minus of input. How do we do it? So what I'm going to do is this. I'll take the previous circuit. I'll give a twist at its output. Whatever was at the negative of the previous output, it is at the positive now. Whatever was at the positive, it is now at negative. So the new output is going to be negative of the previous output. Now, instead of drawing it like this, let me make the circuit a little more compact and simple. Let's do the analysis. In the first half cycle, input is positive. We get positive here and negative here. The diode will get positive here and negative here. Diode is going to be in reverse bias. We can model it as an open circuit. Here, since the circuit is open, no current will flow through the resistance R and therefore the output is going to be 0. Again, in the second half cycle, input voltage is 0. We'll get negative here and positive here. So the diode will get negative here and positive here. It is going to be forward biased. So in the circuit model, we can model the diode as a closed circuit like this. Here the entire input will be dropped across the resistor. Since we are taking the twisted output, the output we get will be equal to negative of the potential across the resistor. Potential across the resistor is the input voltage. So V output is going to be negative of the V input. So in the positive half cycle, output is 0. In the negative half cycle, it is negative of the input voltage. Therefore, we will get the output voltage like this. Let's go to the next challenge. Again, my input is the same, and this is the output I want. For positive cycle, I want output to be equal to input. For the negative cycle, I want the output to be negative of the input. How do we do this? Well, this is my idea. I know how to get only the positive half cycle like this. All I have to take is a half wave rectifier circuit. I also know how to get an output that looks like this. All I have to do is reverse the direction of the diode and take the twisted output like this. Output of the first circuit gives me the positive half cycle. Output of the second one gives me the negative half cycles. If I add both of them, this is what I get. And this is exactly the output I want. So maybe if I add the two circuits together, I will get a new circuit that will give me the required output. So our job is now to find out what will the combination of these two circuits look like. Let's give it a try. I want to call this diode D1 and this one D2 so we can identify them later. Wherever is the positive of the output taken from, I'll call that point A. Wherever is the negative taken from, I'll call the point B. In the second circuit, positive is taken from this point, so this will be our A. Negative is taken from this point, so this will be our B. To get the combined circuit, first I will take the resistor across which we are taking the output. In the first circuit, A is connected to the N side of the diode. P side of the diode goes to positive terminal of the input. Let us show that over here. In the second circuit, A is connected to N side of the diode. P side of the diode is connected to negative terminal of the input. Let us show that also in the circuit over here. Now we have to figure out what happens to the point B. In the first circuit, B is connected to negative of the input. In the second one, B is connected to positive of the input. How does this work? We could also think of it like this. In the first circuit, B is at a point that is more negative than this point. In the second circuit, it is at a point that is more positive than at this point. I have already shown this point over here, and this point is over here. Assume that I take a point in between these two points and connect B to there. Let me show you how this works. Assume this point has plus 5 volt. This point has 0 volt. Obviously, with respect to the plus 5 volt, 0 volt is negative. The midpoint has 2.5 volt. Now, when compared with this point is at a lower potential. But when compared with this point, it is at a higher potential. The idea sounds good, but how do we implement this? For that, we have to take into consideration where the input is actually coming from. We know the power is actually supplied in the form of AC. Then we use a step down transformer to step down the voltage. The output of the transformer is given as an input to a rectifier. It will look something like this. Now we will connect the point B to the middle of the secondary wiring of our transformer like this. This will make the point B more negative than this point and more positive than this point. One more thing is, this is not how an engineer should be drawing a circuit. We have to draw it in a better way. Let's make sure all the connections are still the same. The center of the transformer is connected to point B. N side of diode 1 is connected to A. N side of diode 2 is also connected to A. Output is taken across the resistor R. This is the same circuit. One more thing I can see is we are taking the output across the resistor and the resistor is connected like this. Technically, the resistor is between this point and this point. Why do we have to make the circuit so complicated? Why can't we just put the resistor here like this, directly between the 2 points, and take the output across the resistor like this? Now, which point is A and which point is B? Remember, the N side of D1 and N side of D2 was connected to point A, so this will be our point A. Center of the transformer was connected to point B, so this will be our point B. Again, A is the point from where we took the positive of the output. So this is where we'll mark positive. B is the point from where negative of the output is taken. So we mark here negative. Now that we have our circuit, let us do the analysis to make sure we get our required output. Let us take the first half cycle, which is positive. First diode will get positive here and negative here. It will be forward biased. We can replace it by a closed circuit. The second diode will get negative here and positive here. It is going to be reverse biased. So we can replace it by an open circuit. Since the circuit is open here, the lower loop will not have any current passing through it. So let us ignore that part. Since point B or the middle of the secondary winding of our transformer has lesser potential than this point, let us consider it as our new negative. Now, the positive of the input is directly connected to the positive of the output. Negative of the input is connected to the negative of the output. So, in this case, V out is equal to V in. Let's take the second half of the cycle. Voltage is negative. The first diode will get negative potential here and positive potential here. So it is going to be reverse biased. We can replace it by an open circuit. Second diode will get positive potential here and negative potential here. It is going to be forward biased. Let us model it as a closed circuit. Again, since the circuit is open here, no current will pass through the upper loop. Let us ignore it. Now, since point B has a higher potential than this point, let us consider that as our new positive of the input. We can see that positive of the input is directly connected to negative of the output. Negative of the input is directly connected to the positive of the output. So in this case, V output is actually negative of the V input. Let us plot the result on the graph. For positive half cycles, output is equal to input. It will look like this. For the negative half cycles, output voltage is the negative of the input voltage. On the graph, it will look like this. When we only got half of the cycle in the output, we call the circuit half wave rectifier. Here we have both cycles in the output, so we call this a full wave rectifier. Not just that, since we are using the technique of sender tapping, this is called a sender tapped full wave rectifier. Now everything is clear, but there is something that doesn't make sense to me. I have marked V0 as the peak value of my input. V0 is also the peak value of my output. See, the AC supply is given as an input to the primary winding of our transformer. The transformer then steps it down to a smaller peak value. So we get something across the secondary winding over here. In the positive half cycle, we only utilize half of it. In the negative half cycle also, we only use half of it. So shouldn't the peak of the output be half of that of the input? This thought process is correct, but there is an important clarification to make here. What we call V input is not the voltage we get across the secondary winding of the transformer. In the first half cycle, we take the input across this. So whatever we get here is considered our input. Whatever is its peak is V0. So the output that looks like this will also have a peak equal to V0. In the second half cycle, input is taken across these 2 points. So whatever you get here is considered the input. Its peak is V0. So the output that looks like this will also have a peak V0. When we combine them, we get an output waveform like this whose peak is V0. So V naught is not the peak of the entire waveform that is coming out of the secondary winding. It is what we use for our individual half cycles. Let us now find the peak inverse voltage or the peak reverse voltage. It is the maximum input voltage a diode in a circuit can withstand in the reverse biased condition without breaking down. We can denote it as PIV. Let us take the circuit when the input is negative. Since the input is negative, the first diode is now an open circuit and the second one is in closed circuit. First diode is in reverse bias, so let us take the potential across it and call it V. Maximum value V can get will be the peak inverse voltage. We get negative here and positive here. V naught is the peak value of whatever is the waveform we get between these 2 points. Again, since the input is negative, we get positive here, and since this point is more negative than that point, we consider that as our negative. V naught is the peak of whatever is the voltage we get here. In the lower loop, we can see there is a resistor and it is directly connected to the input. Positive goes to positive, negative goes to negative. So we can write from the lower loop, potential across the resistor VR is equal to V naught. This is when the input waveform is at its peak, the maximum possible value. Now see the upper loop. We have minus V naught plus here. We have minus VR plus across the resistor. And we have minus V plus across the diode. Let us use KVL. Using KVL in the upper loop, we can write V naught minus V plus VR is equal to 0. If I go clockwise like this, V naught goes from positive to negative, V goes from negative to positive, VR again from positive to negative. That is why in the KVL equation, V naught and VR have the same sign. I have taken it as positive, so V has the opposite sign, negative. We already got VR as V naught. So we get V naught minus V plus V naught is equal to 0, or V is equal to 2 V naught. That means when the input is at its peak, potential drop across the diodes is 2 V naught. Which means our diodes should be able to withstand at least a potential of 2 V naught. So to ensure the safe operation, we have to choose a diode that has PIV rating greater than or equal to 2 V naught. Let's go to the next design challenge. We have to remove the center tapping. Center tapping is the mechanism of taking the potential from the center of the secondary winding of the transformer. The problem with this technique is it makes our device costly. Another problem is that the peak reverse voltage is 2 V naught. It's too high. In the half wave rectifier, it was only V naught. Another problem is we cannot use the entire secondary waveform. We are using half of it in each of the half cycles. Also, the two halves of the secondary winding should be perfectly symmetrical. Otherwise, the output of the first half cycle and the output of the second half cycle will not have the same peak voltage. Finally, using center tapping makes our circuit more complex and more costly. So let us design a new circuit that gives us a full wave rectifier output without the need of center tapping. This is what I am going to do. I will take the two circuits that gave me individual outputs for the positive half cycle and the negative half cycle. This one gives me the first half cycle and this one gives me the second half cycle. Now, I am going to add two extra diodes, one for each of these circuits without affecting the output. Let us check if these affect the output or not. For the first circuit, when the input is the first half cycle, we get positive here and negative here. So positive here and negative here means this diode will be forward biased. Negative here and positive here means this one is also in forward bias. In the negative half cycle, we get negative here and positive here. This one is going to be in reverse bias. This one will get positive and negative. This is also going to be reverse bias. So for the positive half cycle, both of them will be in forward bias. Both of them can be replaced by a closed circuit. V output will be equal to V input. In the negative half cycle, both of them are going to be reverse biased. Both of them will be replaced by an open circuit in the circuit model. V output will be equal to 0. So output is going to exactly look like this. In the second circuit also, for positive half cycle, both of them will be reverse biased. So output will be equal to 0. For negative half cycle, both of them will be forward biased. So output will be equal to negative of the input. Output will exactly look like this. Even though these two diodes doesn't do anything to the output, these are going to help us a lot in removing the sender tapping. Just like we did earlier, let us try to combine these two circuits. I have given the diodes different colors so we can identify them later. Before we combine them, I am going to draw both these circuits in a weird way. I'll draw the first one like this. Let's take a moment to check if the connections are the same. Positive of the input goes to the diode, reaches point A, goes through the resistor, reaches the point B. Again a diode goes to the negative. In a similar way, let us draw the second circuit also. Positive of the input reaches the diode, reaches point B, goes through the resistor, reaches point A, again through the diode, reaches negative. I'll give you a moment to check this for yourself. Okay, now we have to combine these circuits. All I'm going to do is this. I will take this circuit, place it exactly over here. Why does it work? See, what is this point? It is connected to the positive of the input. This point is also positive of the input. So they are the same point. What is this point? B. What is this point? B. They are the same point. This is A. This is also A. This is where the negative of the input comes. This is where the negative of the input comes. So these are the same points, which means we can just connect them together like this. That gives us this circuit. This is much less complicated than the center tapped version. Here we can say that the four diodes are connected in a square shape or a bridge shape. Because of this, we call this the full wave bridge rectifier. Now that we have the circuit, let us check if it actually works. We have to do the analysis. First, I'll do the analysis taking the ideal diode model. In the first half cycle, voltage is positive. So we get positive here and negative here. This diode will get positive here and negative here. This one will get positive here and negative here. This one will get negative here and positive here. And finally, this one will get negative here and positive here. Now, this will make these two diodes forward biased and these two diodes reverse biased. If you draw the circuit model, this is how it will look like. I have modeled all the diodes in forward bias as a closed circuit and all the diodes in reverse bias as open circuits. Since it is open here, no current will flow through this branch. Also, since it is open here, no current will flow through this branch. So in this circuit model, we don't really need them there. Let us remove them. Now, positive of the input is directly connected to positive of output. Negative is directly connected to negative. So V output is equal to V input. Let us plot this on our graph. For the next half cycle, voltage is negative. So this diode will get negative here and positive here. This diode will get negative here and positive here. This one will get positive here and negative here. And the last one will get positive here and negative here. Now, I know you already know this, but let me ask you a silly question. I have marked this point to be having negative potential, this point to be having positive potential, but they are the same point. Why is this positive and this negative? We have put positive here and negative here to show that P side of this diode is more positive than its N side. We have put positive here and negative here to show that for this diode, its N side is at a higher potential than its P side. So yes, these two are the same point. They have the same potential, but it is more negative compared to this point and it is more positive compared to this point. Again, let us see which ones are forward biased and which ones are reverse biased. I can see this is reverse biased. This is also reverse biased. This is forward biased. This is also forward biased. So let us draw the circuit model. Since it is open here, no current will pass through this branch. Let us remove it. Also, since it is open here, no current is going to flow through this branch also. Let us remove that. Now, negative of the output is taken from the positive of the input. Positive of the output is taken from the negative of the input. So, V output is negative of the V input. If we plot it on the graph, this is what we get. And this is exactly what we wanted. One thing we can see is the output waveform is repeating at half the time when compared with the input. So time period of the output is half of that of the input, or frequency of the output is double as that of the input. Now let us find the average value of the output of a full wave rectifier considering the ideal diode model. We have to calculate the average value of the output for one full cycle of the input. That is from 0 to t. So we can write V average is equal to integral from 0 to 1 time period of V output dt divided by integral from 0 to 1 time period of dt. In the numerator, we have to integrate the output voltage across one time period of the input voltage. That is from here to here. It is the same as taking the integration from 0 to t by 2 two times. So we can write it like this. 2 times integral from 0 to t by 2 V output dt divided by integral of dt is t. We have to give the limit from 0 to t. So that will just become t. Let us write it there. Again, on the numerator, we are integrating the output from 0 to t by 2. From 0 to t by 2, this is what we have. It is equal to the input, which is V naught sine omega t. So we can replace V out over here by V naught sine omega t. V naught is a constant. Let us take it out of the integration. Let's put the t also over here. So this becomes 2V naught divided by t. Integral of sine omega t is minus of 1 by omega cos omega t. Let's give the limit from 0 to t by 2. Now this becomes minus 2V naught divided by omega t. Giving the upper limit, we get cos of omega t by 2 minus giving the lower limit, we get cos of 0. Now we know omega is 2 pi divided by t. So if we take the product of omega and t, we get 2 pi. Over here we have omega t, we can write it as 2 pi. Over here also we have omega t, we can write it as 2 pi. 2 and 2 can be cancelled. 2 pi divided by 2 is pi. Now this becomes minus V naught divided by pi multiplied by cos pi is minus 1, cos 0 is 1. Minus 1 is minus 2. Negative and negative gets cancelled and we get 2V naught divided by pi. So we can write average value or the DC value of the output is 2V naught divided by pi or 0.637 times V naught. V naught is the peak value of our input. Let us now plot the input-output characteristics of a full wave rectifier considering the ideal diode model. This is the output we get. For all the negative half cycles, that is, for V input being less than 0, V output is equal to negative of the V input. Also, for all the positive half cycles, that is for V input being greater than 0, V output is equal to V input. In the first case, if you take the ratio V output divided by V input, you get -1. In the second case, if you take the same ratio, V output divided by V input, you get 1. We are going to plot a graph with V output on the y-axis and V input on the x-axis. In that case, the ratio V output divided by V input will be the slope of the graph. When V input is negative, it is -1. When V input is positive, it is +1. So the graph will look like this. Let us now plot the output of a full wave bridge rectifier when the constant voltage model of a diode is taken. In the first half cycle, input is positive. So these two diodes are going to be forward biased. These two are going to be reverse biased. The reverse biased ones, as always, can be replaced by open circuits. The forward biased ones can be replaced by a cell of potential equal to their knee voltage. Now, no current passes through this branch and no current passes through this branch. So we don't really need them in the circuit model. Let us remove them. Let's redraw the circuit in a better way. Now we can use Kirchhoff's voltage law to write the output voltage. We have V in going from negative to positive, Vk going from positive to negative. So we can write V in minus Vk. V out goes from positive to negative, so we have to write minus V out. As we move on, the next Vk is also from positive to negative with opposite polarity of the input, so minus Vk is equal to 0. From this we can write V output. It is V input minus 2Vk. But this is only when the two diodes are switched on, right? We are taking the constant voltage model, so the diode takes at least a potential of Vk so that it is switched on. We have two diodes to switch on, so the input should at least be 2Vk so that the diodes will both be switched on and the output will be V in minus 2Vk. Until then, output is going to be equal to 0. If I plot this on the graph for all the positive half cycles, this is how it will look like. Let's take a closer look. Until V input becomes equal to 2Vk, output is 0. After that, output becomes V input minus 2Vk and it goes like this. At this time, input again becomes equal to 2Vk. After that, input is less than 2Vk, which means the two diodes will go to reverse bias and output will be 0 again. Let us do the same analysis for the negative half cycles. In that case, these two diodes will be in reverse bias. These two will be in the forward bias. The ones in the reverse bias can be modeled as an open circuit. The ones in forward bias can be modeled as a cell with potential equal to their knee voltage. Since the circuit is open here and here, no current is going to flow through both of these branches. Let us remove them. Let's draw the circuit in a better way. If you want, take a second to check if all the connections are the same. Now, we can use Kirchhoff's voltage law to write an expression for V output. We will start from this point. V input is from negative to positive. So I will write V input. There is a potential drop of Vk also from negative to positive. So I will write plus Vk. As I go on, here I have negative to positive. So I will write plus V out. Going on, again there is a potential drop of Vk, negative to positive. So I will write plus Vk. All are in the same direction. This is equal to 0. So here I can write V output is negative of V in plus 2Vk. Here also we have to keep in mind that this is only when both the diodes are switched on. We have to switch on two diodes of new voltages Vk. That means the input has to be at least equal to minus 2 Vk so that the output will be non-zero. Let's mark it on the graph. Let's take a closer look. Unless the input reaches this point, that is corresponding to minus 2 Vk, output is going to be 0 because the two diodes have not switched on. After they have switched on, output voltage is negative of V in plus 2 Vk. V in looks like this. If you add 2 Vk to it, it will become less negative and you will get something that looks like this. If you take the negative of it, you get this. Same thing on all the negative half cycles. Let us now write an expression for the average value of output for a full wave rectifier when we consider the constant voltage model. In the ideal diode model, we got it as 2 by pi times the peak value or 0.637 times the peak value. Here also, the output has a very similar shape to the output in the ideal diode model. So we can use the same equation. The only difference is peak value is not V0 anymore, it is V0 minus 2 Vk. So we can write here the average value or the DC value of the output over one cycle of the input is 2 divided by pi multiplied by the peak value, that is V0 minus 2 Vk, or 0.637 times the peak value V0 minus 2 Vk. Let's now solve a problem. Assuming the constant voltage model for the diodes, plot the input-output characteristics of a full wave rectifier. Let us first take the output waveform of the full wave rectifier. Now, whenever the input is between plus 2 Vk and minus 2 Vk, output is 0. You can see that over here. Input is plus 2 Vk here, input is minus 2 Vk here. In between, it takes so many values, but at all these places, output is 0. Here also, when input is between plus 2 Vk and minus 2 Vk, output is 0. Let us write it down. To plot the input-output characteristics, let us take a graph with V out on the y-axis and V in on the x-axis. We saw that when the input is between plus 2 Vk and minus 2 Vk, output is 0. Let us plot it on the graph. Now, when V input is positive and greater than plus 2 Vk, output is V input minus 2 Vk. Also, when input is negative and lesser than minus 2 Vk, output is negative of V input plus 2 Vk. This can also be written as minus V in minus 2 Vk. Both these equations remind me of the equation of a straight line. We are taking V output on the y-axis and V input on the x-axis. So whatever is the coefficient of V input will be the slope of the graph. Here it is 1. So when V is greater than 2 Vk, slope is plus 1. In the second case, coefficient of V input is minus 1. So here slope is minus 1. We can plot them on the graph like this. Let us solve another problem. Here we have to determine the output waveform for the network given. Also calculate the output DC level and the required PIV for each diode. Input is 1 cycle of a sinusoidal voltage. Peak value is 10 volt. We have a bridge network here. The only difference I can see is instead of 2 diodes over here, we have 2 resistors of 2 kilo ohm. Let us do the analysis. In the first half cycle, voltage is positive, so we get positive potential here, negative potential here. When you consider this diode, it will have a higher potential on its P side than its N side. So it is forward biased. And when you consider this diode, it will have a higher potential on its N side rather than on its P side. Diode in the forward bias can be modeled by a closed circuit, and the one in the reverse bias can be modeled as an open circuit. Since the circuit is open over here, no current will pass through this branch. Let us remove it. Now the current will pass in this direction. It will go like this, reach over here at the junction. From there it will split. One part will go through the blue resistor and then through the violet resistor. The other part will go through the orange one. Let us draw this circuit in a better way. Output is taken across the blue resistor. Let us draw this circuit in a better way. This is much simpler to analyze. Now we need an expression for V output. Since the blue resistor and the violet resistor are in series, V input will be divided between them equally. We can write voltage across the blue resistor, V out is V in divided by 2. Let us do the analysis for the second half cycle of the input. In the second half cycle, voltage is negative, so we'll get negative potential here and positive potential here. When you consider this diode, it will get a lower potential on its P side than on its N side. It will be reverse biased. The other diode will get a lower potential at its N side than at its P side. So it will be forward biased. Let us replace the forward biased diode by a closed circuit and the reverse biased one by an open circuit. No current will pass through this branch, so let us remove it from the circuit model. Let's see what happens to the current. Current passes through this point and reaches this point, which is a junction. From here, some part will go through the blue resistor and then through the orange resistor and then goes to the negative terminal. The rest of the current will pass through the violet one and go to the negative terminal. Output is still taken across the blue resistor. Let's draw the circuit in a better way. This circuit looks exactly like what we got previously, but there is a very minute difference. Previously, positive of the output is taken from positive of the input. Negative comes from the negative of the input. Now it is opposite. Negative is taken from the positive. Positive is taken from the negative. So here, V output is going to be negative of V input divided by 2. It's almost like we are taking the twisted output. To plot the output, let's take a graph. In the first half cycle of the input, output is V in divided by 2. So we will get this. Since it is half of the input, its peak value will be half of the input peak value. That is 5 volt. For the second half cycle of the input, we get minus V in by 2. But the second half of the input is already negative. So if you take its negative, this is what you get. This is the output of a full wave rectifier. So we know how to find the DC value. VDC is 2V0 divided by pi. That is 2 times V0 is 5 divided by pi. And this is 3.18 volt. The question also says to find out the PIV of each diode. Both diodes are connected at similar conditions, so their PIV is going to be equal because of symmetry. So let us take one of them and find their PIV. To find PIV, we have to give negative potential to one of the diodes. So let us assume we get negative here and positive here, which means this one will be in reverse bias, this one will be in forward bias. Let's replace this one with an open circuit and this one with a closed circuit. Now we have to find out what is the maximum potential that comes across this diode over here. Now let's consider the potential across the diode to be V. You can see that the diode is connected exactly across the resistor over here. So whatever is the potential across the resistor, that will be the potential across the diode. Potential across that resistor is V output. The maximum potential V output can get in this case is 5 volt. So the PIV rating of our diode should at least be equal to 5 volt so that we can operate the circuit without the diodes getting damaged. In the second half cycle, the exact opposite will happen. This will be closed and this will be open. Same condition. Maximum voltage that drops across the other diode is also 5 volt. So its PIV rating should also be greater than or equal to 5 volt. Let's take another problem. We have to plot the currents carried by each diode in a bridge rectifier as a function of time. We have to use the constant voltage model. Let's do the analysis for the first cycle. Let's do the analysis for the first half cycle. Let us take another problem. We have to plot the currents carried by each diode in a bridge rectifier as a function of time. Use constant voltage model. Let's do the let's do the analysis for the first half cycle. Input is one period of a sinusoidal voltage. Maximum its peak value is V naught and we have the bridge rectifier circuit. Let's do the analysis for the first half cycle of the input. In the first half cycle, voltage is positive, so we get positive potential here, negative potential here. Obviously, this diode is going to be forward biased and this one is going to be reverse biased. Let's model them accordingly using an open circuit and a closed circuit. Let's model them using a let's model them using a closed circuit. Let's model them using a closed circuit and an open circuit. The reverse biased one the reverse biased one can be replaced by the reverse biased one can be replaced by an open circuit. The forward biased one can be replaced by a cell of potential equal to its knee voltage because we are taking the constant voltage model. The same way, this diode will be reverse biased and this one will be forward biased. Let's replace this one with a cell of potential equal to its knee voltage and this one by an open circuit. Since no current is passing through them, let's remove this branch and this branch. Now this is a simple circuit. Let's draw it in a better way for analysis. As we go clockwise, there is V input, Vk in the opposite direction, V out in the opposite direction, Vk again in the opposite direction. So we can write using KVL, V input minus Vk minus V output again minus Vk is equal to 0. From here we get V output is V input minus 2Vk. Now V output is the potential across the resistor. So using Ohm's law, we can find out what is the current flowing through the resistor. But whatever is the current flowing through the resistor is exactly what is flowing through the diodes. The diodes that are represented by the cells right now. So we can write current through the first diode is equal to the current through the second diode. They are both equal to the current through the resistor, which is potential across it divided by its resistance. Potential across it is V output. So V input minus 2Vk divided by R. How about the current through the other two diodes? The other two diodes are in reverse bias. So we can write ID3 is equal to ID4. This is equal to 0 ampere. No current is flowing through them. Now let's do the analysis for the second half cycle of the input. In the second half cycle, voltage is negative. We get negative potential here, positive potential here. These two diodes will be in reverse bias. These two will be in forward bias. The ones in forward bias can be modeled by a cell of potential equal to their knee voltage. The ones in reverse bias can be modeled as open circuits. No current will pass through these two branches. Let us remove them. Now the circuit is pretty simple. Let's redraw it in a better way. Let us use KVL to write an expression for output. We'll start from here and go clockwise. Input is from negative to positive. Then we have Vk from negative to positive itself. V out also from negative to positive. Again Vk from negative to positive. So we can write V input plus Vk plus V out plus Vk is equal to 0. Or we can write V output is negative of V in plus 2Vk. Again, V output is the potential across the resistor. So we can find the current flowing through it using Ohm's law. The same current is flowing through the diodes also. The diodes that are represented by the cells now. So we can write current through the third diode is equal to current through the fourth diode. They are both equal to current through the resistor right now, and it is V output divided by R, or minus of V in plus 2Vk divided by R. How about the other two diodes? They are reverse biased, so current flowing through them is 0. Let us take two graphs. One to plot the current passing through diodes 1 and 2, other one for diodes 3 and 4. For diodes 1 and 2, in the first half cycle, current passing through them is V input minus 2Vk divided by R. V input is sinusoidal. Subtracting 2Vk from it will lower its value, but it will still be sinusoidal. Dividing it with R will again lower the value, but it is still going to be sinusoidal. So this is what we get. Current will be maximum when the input voltage is maximum. So the maximum current we get is V0 minus 2Vk divided by R. Now for the second half cycle, current through them is 0. When we consider diodes 3 and 4, in the first half cycle, they have 0 current through them. In the second half cycle, they have a negative of V input plus 2Vk divided by R. In the second half cycle, input is already negative. So if you add 2Vk to it, its magnitude will become lesser. It will become less negative. You will get something that looks like this. Now you are dividing it with R. Its magnitude will be scaled by that also. You are also putting a negative to it. So negative of this is this. On the graph, it will look like this. This current will be maximum when the input is at its negative peak. That is, V input is equal to minus V0. If we calculate the peak value, we'll get negative of minus V0 plus 2Vk divided by R, or V0 minus 2Vk by R, just like what we got over here. In the first case, since voltage is positive, current flowed in this direction. That is from point A to point B. In the second case, since voltage is negative, current flowed in this direction. But interestingly enough, this is also from point A to point B. That is why in both graphs, we got the same direction for current. Now let's find out the peak inverse voltage or peak reverse voltage required for the diodes used in a full wave bridge rectifier. Let's consider the case when V input is negative. The circuit model will look like this. These two diodes are modeled as open circuits because they are in reverse bias. These two are modeled as closed circuits because they are in forward bias. Let's take the potential drop across this diode as V. Now you can see this is directly connected across the resistor. That means V is equal to VR. Resistor is where we are taking the output from. So whatever is the maximum value of the output, that is the maximum value of VR. Maximum value of the output in the full wave bridge rectifier is V0, the maximum value of the input. So we can conclude the maximum potential that will ever be across the diode is V0. So the PIV rating of the diode should at least be equal to V0 so that we can use the circuit without damaging the diode. PIV rating should be greater than or equal to V0. Let us write this down. At the peak value of the input, potential across the resistor will be peak value of the input, that is V0. From this loop, we can see potential across the diode is equal to the potential across the resistor, whose maximum value will be V0. This is going to be the same for this diode also. If we mark the potential across it, we get plus minus V, and that will also be equal to VR. Maximum value of VR is V0. So PIV rating of this diode should also be V0. Similarly, if you take the other half cycle of the input, you can see these two diodes will also be in the same condition. For a full wave bridge rectifier, we have to use diodes with PIV rating greater than or equal to V naught. V naught being the peak value of our input. This is the output we got for a full wave rectifier. This has all the problems a half wave rectifier had at this stage. The circuit does not produce a useful output. Unlike a battery, the output varies considerably with time. It cannot be used as a power supply to electronic devices. The only advantage it has over the half wave rectifier is that it uses both the half cycles of the input instead of just one. So, just like we did before, let us try taking the output across a capacitor. Rather than connecting the capacitor directly between these 2 points, I have connected it like this. It will be easier for the analysis this time. Let us start by taking what happens to the input from 0 to T by 4. Input is positive, so this diode is going to be forward biased. This one is also going to be forward biased. These two will be reverse biased. So we can model the circuit like this. I removed the diodes in reverse bias and I have kept the diodes in forward bias as closed circuits. Now, since positive potential is here and negative is here, current has to flow in this direction. Obviously, current cannot flow through a capacitor because the two plates are not touching. So what is actually happening is electrons in this plate of the capacitor will flow in this direction, go through the voltage source, go through here and reaches the other plate. Since electrons are flowing in this direction, current is flowing in this direction. So this plate will become positively charged, this plate will become negatively charged. So basically what is happening between 0 and T by 4 is that the capacitor is getting charged. Since there are no other devices in this circuit model, entire input is going to be dropped across the capacitor. So when the input reaches its maximum value, potential across the capacitor will also reach its maximum value. Let us show it on the graph. Now after T by 4, input has to decrease from the peak value to 0. Since the input is decreasing, obviously the output cannot increase, conservation of energy. So that is not an option. Question is, when the input decreases, will the output also decrease with the input? Our output is the potential across the capacitor. It has positive charges here and negative charges here. If the potential across the capacitor is decreasing, that means the capacitor is discharging. Since the positive charges are here, for the capacitor to discharge, current has to flow in this direction. To see how this is not possible, let us bring back the two diodes that are in forward bias. The other two diodes are in reverse bias. They are open circuits, so definitely current cannot flow through them. That is why I only took the two diodes that are in forward bias. Now, if the current has to flow in this direction, that means current has to flow from the N side of the diode to the P side of the diode, which is impossible. That means the capacitor cannot discharge. So the only option left is capacitor remains charged and the potential across it remains constant. Let's plot it on the graph. Now input is becoming negative. Let's see what happens in that case. When input becomes negative, these two diodes will go to reverse bias and these two will go to forward bias. Let's update the circuit model accordingly. These two are the forward biased diodes, so I kept them. The other two are reverse biased, so I removed them. Again, this plate has positive charge, this plate has negative charge. So if the capacitor has to discharge, electrons from this plate have to go to this plate. That means current has to flow in this direction. Current has to flow from the N side to the P side of this diode, which is not happening. So even now, the capacitor will not get discharged. So the capacitor will remain charged, which means the potential across it will remain constant. We can plot it on the graph like this. Now, what happens in the next positive half cycle? Input is increasing from 0 to maximum value again. Since input has become positive, we have to update the circuit model again. These two will again go to forward bias and these will go to reverse bias. Right now, the potential across the capacitor is the maximum value, which is V naught. On the other side, input is increasing from 0 to its maximum value, it is V naught. The maximum value input can get is V naught. So input throughout this time is going to be less than or equal to V naught. The voltage that it gets on the P side is always going to be lesser than what it already has on the N side. For the other diode also, the voltage that it gets on the P side is always going to be less positive than what it gets on the N side. So from now, they are always going to be in reverse bias. That means once the capacitor is charged, it is never going to discharge. The output is never going to change from V naught after that. Let's plot it on the graph. So once the capacitor is charged, it does not have a path to discharge. That gives us an output voltage that looks like this. Now, this is for the ideal diode model. Let us see what happens for the constant voltage model. The first difference is current will not start flowing unless two of the diodes are switched on. That is, the input has to be at least equal to 2 Vk so that the capacitor can start charging. Until then, V output is going to be 0. Let us plot that on the graph. Now, once the two diodes are switched on, the capacitor will start charging. But the maximum potential the capacitor can have across it will not be V naught, it will be V naught minus 2 Vk. Because there will be a drop of Vk potential on each of the diodes that are in forward bias. Let's plot that on the graph. Now, once it is charged, the capacitor will not be discharged anymore. So the output is going to be constantly at V naught minus 2 Vk. Now, our output is not varying with time, so we can call it DC. But just like we discussed in the previous video, we have to connect this to a device. We have to use this to charge a device. Let's model the device that we are going to charge as a resistor. Then this is the circuit model we have. Along with the capacitor, we also have a resistor. The resistor is the load or the device that we are trying to charge using the rectifier. Let's try to plot the output considering the ideal diode model. The first half cycle, the first half cycle is positive, so two of the diodes are going to be forward biased, the other two will be reverse biased. Let's remove the reverse biased ones because no current is going to flow through their branches. The circuit looks a little bit weird. Let me draw it in a better way. This can be taken as our circuit model for the first half cycle of the input. Both of these diodes are in forward bias. Let us replace them by closed circuit. Current will flow in this direction and the capacitor will start getting charged. As the capacitor gets charged, voltage across it also increases. Let's plot it on the graph. At T by 4, the capacitor is completely charged. Output voltage is equal to the maximum value of input voltage, which is V naught. The capacitor gets positive charge on this plate and negative charge on this plate. After T by 4, input voltage has to decrease from its maximum value to 0. Since input is decreasing, obviously output cannot increase. It also cannot decrease because for it to decrease, the capacitor will have to discharge through a diode, making current flow through it from the N side to the P side, which is not possible. So without the resistor here, the capacitor would stay charged. Voltage across it will remain constant. But in this case, we have a resistor here. So the electrons from this plate of the capacitor will be able to flow through the resistor to the other plate. Current will be able to flow through the resistor like this. Let us assume that the capacitance is really large so that the time constant of this RC circuit is really large, which means the capacitor discharges really slow. We can assume that the discharge is linear. We have discussed this concept in detail in the previous video. Since the capacitor is discharging linearly, the voltage across it will be dropping linearly. Let us show it on the graph. This is what happens in the first half cycle of the input. Let's bring back our original circuit. The second half of the cycle is negative. So these two diodes will be in forward bias. These two will be in reverse bias. Let's remove the ones in reverse bias. Again, the circuit looks weird, so I'm going to draw it in a better way. There is a twist happening here. I have shown it over here. This is our circuit model for the second half of the input. That is when the input is negative. Both these diodes are in forward bias. Let us replace them by closed circuits. Again, this is the circuit model for the negative half cycle of the input. So the input here looks like this. On top of that, there is a twist. So the input is twisted, which means the actual input we get over here is this. So to make the circuit model simple, instead of taking the input like this and then twisting it, let us remove the twist and take the input like this. I remove the twist. In the graph over here, I will change the input from this to this. Now the input is increasing from 0 to its maximum value. Meanwhile, the capacitor was decreasing from its maximum value. At this particular point, that is at T by 2, capacitor voltage is higher than the input voltage. So when you think about the diodes over here, output voltage is what they get on the right side. Input voltage is what they get on the left side. Since output voltage is higher, they will remain in reverse bias. That means the capacitor will keep discharging through the resistor. So the graph will go like this until this particular point. At this particular time, input voltage has increased and it is over here now. Capacitor voltage has decreased and it is also having the same value. The diodes have equal potentials on both sides. After that, the input voltage is increasing. That means both of the diodes will now become forward biased. They will again start conducting. They will again start charging the capacitor. That will make the potential drop across the capacitor increase. It will look like this on the graph. Now the capacitor voltage is here. Input voltage is also here. But input voltage is about to decrease, which means the diodes will go back to reverse bias, which means capacitor will once again try to discharge through the resistor. Since capacitance is really high and the discharge is linear, this is how the voltage will drop. Once again, at this point of time, input and voltage across the capacitor, which is the output, becomes equal. After that, the input is increasing. Diodes will go to forward bias. Capacitor will again charge. This keeps happening cycle after cycle. If you think about it, without the capacitor, this is the output we had. Now we have this. So technically, we are comparing the new output with the old output. And the new output is much smoothened than the last one. So we call the capacitor a smoothening capacitor. Let's bring back the circuit to normal and see how the output will look like if we take the constant voltage model. The first difference is that the capacitor will not start charging unless two of the diodes are in forward bias. For that, the input has to be at least equal to 2 times the knee voltage. Also, when the input reaches the peak value V0, V output will not become V0, it will be V0 minus 2 Vk because of the Vk drop across the two diodes in forward bias. Other than that, the rest of the mechanism is the same and the output will look like this. In this case, the capacitor will again start charging at this point of time where the difference between the capacitor voltage and the input voltage is 2 Vk, so that both the diodes will be able to switch on, conduct current and charge the capacitor. Another important thing is, here you can see the ripple is happening in every half cycle of the input. If you remember, in the half wave rectifier, the output voltage looked like this. Capacitor charges in the first quarter of the cycle Then it keeps discharging until the next cycle of the input where the input voltage and capacitor voltage becomes equal again. After that, it recharges. But over here, the recharging happens here itself, that is in the second half cycle of the input. Because of this reason, in full wave rectifier, the ripple frequency is 2 times the frequency of the input. Let's now find the ripple voltage in a full wave rectifier. I have taken the output for a constant voltage model. Let's consider two time points, T1 and T2. The discharge is happening between T1 and T2. So we have to find out the difference between the voltages at T1 and T2. That will be our ripple voltage. Since we have assumed the capacitance is really large and the discharge is linear, we can express the voltage between T1 and T2 like this. V out is approximately equal to the maximum value, which is here V0 minus 2Vk. If we take the ideal diode model, instead of V0 minus 2Vk, you will be writing V0 because that is the peak value then. For linear discharge, V output will be approximately peak value multiplied by 1 minus T divided by tau, tau being the time constant RC. Now, this can be written as V0 minus 2Vk minus V0 minus 2Vk divided by tau multiplied by T. Tau can be written as RC. We have to find out the ripple voltage. That is the difference between voltage at T1 and voltage at T2. We already know the voltage at T1. It is V0 minus 2Vk. So I will write ripple voltage VR is V0 minus 2Vk, which is the voltage at T1, minus whatever is the voltage output at T2. I have to find out the voltage at T2, which is simple because we already have an equation that relates V output to T. V output is V0 minus 2Vk minus V0 minus 2Vk divided by RC multiplied by T. So to get the V output at T equal to T2, all I have to do is replace T by T2, right? Wrong. We went through this before. This is the equation for V output only between T1 and T2. So our initial time is T1. When you are at T2, the time that has passed is this much. It is not T2, it is T2 minus T1. So to get the voltage at T2, you have to replace T by T2 minus T1. Let's do that. So we get V0 minus 2Vk minus of V output at T2 is V0 minus 2Vk minus V0 minus 2Vk divided by RC multiplied by T2 minus T1. V0 minus 2Vk here and V0 minus 2Vk here will get cancelled. There is a negative and a negative that will become positive. So we get VR is V0 minus 2Vk divided by RC multiplied by T2 minus T1. Now, T1 is at the middle of the first half cycle. This is the middle of the second half cycle. So, this much time will be half of the time period. If our capacitance is really high, even higher than what we have over here, the capacitor will discharge even slower. So, the graph will look like this. If the capacitance is even higher, it will look like this. If ideally the capacitance is really large, this yellow point over here will be somewhere over here, even closer to the middle point of the second half cycle. What I'm trying to say is the difference between T2 and T1 can be considered approximately equal to half of the time period. Then we can write VR is V0 minus 2Vk divided by RC multiplied by T divided by 2. T is the time period. We can write it as 1 by frequency of the input. Then ripple voltage becomes V naught minus 2 Vk divided by 2 RCF. Let's put this in a box. If we had taken ideal diode model, instead of V naught minus 2 Vk, you would be writing V naught. That's the only difference. So V naught is the peak value of the input. Vk is the knee voltage of the diode we are using. R is the load resistor, resistance of the device we are trying to charge. C is the capacitor we are using in the circuit. F is the frequency of the input. Now, instead of the resistance of the device we are charging, we have the current drawn by it. We can take V0 minus 2 Vk divided by R as IL or the load current. In that case, VR will be IL divided by 2CF. Let us now solve a problem. Design a full wave rectifier to deliver an average power of 2 watt to a cell phone with a voltage of 3.6 volt and a ripple voltage of 0.2 volt. Input frequency is 60 Hz. First, let me draw the circuit. AC supply is coming. It is stepped down by a transformer. It is given as an input to our rectifier. We also have a capacitor to smoothen the output of the rectifier. And then it is gone to the device that is modeled as a resistor. Here it is given that the cell phone needs an average power of 2 watt with a voltage of 3.6 volt across it. From this information, we can find out its resistance. We can also find its current. I want to find the current. The load current IL will be power divided by voltage across the resistor. That is 2 watt divided by 3.6 ampere. Now let's use the expression for ripple voltage. It is IL divided by 2CF. We have to find out the capacitance. So C is IL divided by 2FVR. IL is 2 by 3.6 multiplied by 1 by 2 multiplied by 1 by frequency is 60 multiplied by 1 by VR is 0.2. This is approximately equal to 23,000 microfarad. Let us now have a comparison between half-wave rectifier, center-tapped full-wave rectifier and full-wave bridge rectifier. The first thing is average DC output voltage. For a half-wave rectifier, it was V0 divided by pi, V0 being the peak value of our input. For a full-wave rectifier, be it center-tapped or bridge rectifier, it is 2 times V0 by pi. We get double the DC output voltage. Next, we have to check the RMS value of our output voltage. Let us first derive it. I have the half-wave rectifier output. I also have the full-wave rectifier output. RMS is root mean square. So first we have to square the output voltage, then take its mean, then take the root. So I can write square of the RMS voltage will be mean of the squared output voltage. Average of the square of the V output will be integral from 0 to 1 time period of square of the output dt divided by integral from 0 to 1 time period of dt. For a half-wave rectifier, in the first half cycle of the input, the output is V0 sin omega t, the input itself. For the second half, it is 0. So we don't have to integrate from 0 to t. We can just integrate from 0 to t by 2. Then we get integral from 0 to t by 2. V output squared is V0 square sine square omega t dt divided by integral of dt is t, giving the limits from 0 to t, we get t. V0 square is a constant. Let us take it out of the integration. Then we get V0 square divided by t integral from 0 to t by 2 of sine square omega t dt. Using trigonometric formula, sine square omega t can be written as 1 minus cos of 2 omega t divided by 2. Let us replace it by that. Let's take the 2 in the denominator out of the integration. Let us take this integral out and evaluate it separately. We can split this into two terms, integral of 1 dt and integral of cos 2 omega t dt. Integral of dt is t. Let's give the limit from 0 to t by 2. Minus integral of cos 2 omega t is sine 2 omega t divided by 2 omega. We have to give the limit from 0 to t by 2. For the first term, giving the upper limit t by 2 and lower limit 0, we get t by 2 minus 1 by 2 omega multiplied by, giving the upper limit, we get sine 2 omega t by 2 minus sine of 0. 2 and 2 gets cancelled. Omega multiplied by t is 2 pi. Sine of 2 pi and sine of 0 are 0. So this whole term becomes 0. Value of the integral is simply t by 2. Let us substitute that over here. Then square of the RMS voltage will be V0 square divided by 2t multiplied by t divided by 2. T and t can get cancelled. So this becomes V0 square divided by 4. We squared the output, we took its mean. Now to get the RMS value, we have to take the root. If we do that, we get VRMS is V0 divided by 2. Now we have to do the same for the output of a full wave rectifier. We have to square the output, take the mean, take the root. Let us take the root later, we'll do the rest of them first. So we can write square of the RMS voltage will be mean of the square of the output. For the full wave rectifier, output for the first half cycle is V0 sin omega t. For the second half cycle, it is minus V0 sin omega t. But it doesn't really matter because we are squaring it anyways. What I mean is this. If we take V out square, for the first half cycle, we will get V0 sin omega t squared. For the second half cycle, we will get minus V0 sin omega t squared. Since we are squaring, these two are equal. So here I can write integral from 0 to 1 time period of V0 square sine square omega t dt divided by integral of dt is t, giving the limit from 0 to t, we get t. V0 square is a constant, let's take it out of the integration. Again, sine square omega t can be written as 1 minus cos 2 omega t divided by 2. We have to find the value of the integral. It will be integral from 0 to t of dt minus integral from 0 to t of cos 2 omega t. We are integrating a cos function across one time period. A cos function across a time period has equal positive and negative area under the graph. If you add them, you will get 0. So this is simply equal to 0. This is integral of dt from 0 to t. It will give you t. So you can replace this integral over here by simply t. That gives us V0 squared divided by 2t multiplied by t. T and t gets cancelled. This is equal to V0 squared divided by 2. To get the RMS voltage, we have to take the root. So VRMS is V0 divided by root 2. Let's write it in the table. For half wave rectifier, it is V0 divided by 2. For both full wave rectifiers, it is V0 divided by root 2. Next, we have to compare the peak inverse voltage. For half wave rectifier, it was V0. For a center tapped full wave rectifier, it was 2 V0. For the full wave bridge rectifier, it is again V0. Next, we have to compare the complexity and cost. A half wave rectifier is simple and inexpensive, but it is not as useful as a full wave rectifier. A center tapped full wave rectifier has moderate cost due to the center tap transformer. For a full wave bridge rectifier, more diodes are needed, but still no sender tap transformer is needed. Let us see how much of the input waveform is used in all of these. In the half wave rectifier, only half of the input waveform is used. In both the full wave rectifiers, both halves are used and we have a smoother output. Next, we need the time period of the output. In the half wave rectifier, time period of the output is equal to the time period of the input. For full wave rectifiers, it is half of it. We also need to find the efficiency of all of this, which we have not calculated, so let us do it now. First, let's do the half wave rectifier output. For a half wave rectifier, only first half cycle of the input is being used. The RMS value of that much is V0 by 2. Average DC output is V0 by pi. So we can write the DC power output like this. Power is V square by the resistance. So here it will be VDC square divided by load resistance. VDC is V0 by pi. So we can write it as V0 squared by pi square RL. Let's also write the AC power input. Since it is AC, we take RMS value of the voltage. Power will be Vrms squared divided by RL. Vrms is V0 divided by 2. So this becomes V0 squared divided by 4 RL. To get the efficiency, we have to take the ratio of DC power output and AC power input. That is the ratio of these two. V0 square and V0 square will get cancelled. RL and RL will get cancelled. So this will become 4 divided by pi square. And this is approximately 40.6%. Let's do the same thing for a full wave rectifier. Here RMS value of the AC input that is being utilized is V0 divided by root 2. DC value of the output is 2 V0 divided by pi. Let's write the DC power output. It is VDC squared divided by RL. VDC is 2 V0 by pi. So we get 4 V0 square divided by pi square RL. We also need the AC input power. Since it is AC, we take RMS voltage. So it is RMS voltage squared divided by RL. Vrms is V0 divided by root 2. So this becomes V0 squared divided by 2RL. To get the efficiency, we have to take the ratio of DC power output and AC power input. That is the ratio of these two. V0 square and V0 square get cancelled. RL and RL get cancelled. What is left is 8 by pi square. And this is approximately 81.2%. Efficiency of the half wave rectifier is 40.6%. For both full wave rectifiers, it is 81.2%. That's all about it for today. See you in the next video. And don't forget to subscribe.